So welcome to lecture 1 of chapter 5, Magnetism and Matter. So some of the commonly known ideas regarding magnetism will be discussed first of all. So the first idea that we are going to discuss is that the earth behaves as a magnet with the magnetic field pointing approximately from the geographic south to the geographic north. That is, the direction of magnetic field is towards the north pole. So when we say something like this, we mean to say that if we consider that this is earth and this is geographic north and geographic south, then we consider that there is a large bar magnet that is placed inside the earth with its north pole facing the south end or the geographic south and the south pole of the magnet facing the geographic north. And due to this, a magnetic field is created which encloses the entire earth as shown. Now, as a result of which, if we suspend a bar magnet freely, then it will start pointing in the north-south direction. So this is the direction of a magnetic field over the surface of earth. So when a bar magnet is freely suspended, it points in the north-south direction. The tip which points to the geographic north is called as the north pole, and the tip which points to the geographic south is called as the south pole of the magnet. So basically I mean to say that if we suspend a bar magnet freely near on the surface of earth, then it will start pointing in the north-south direction with its north pole pointing towards the geographic north. The next fact that must be kept in mind is that the like poles repel each other and the unlike poles attract each other. The like poles repel each other and unlike poles attract each other. The next fact that we establish is that for a magnet, monopole do not exist. When I say monopole do not exist, then I mean to say that if there is a bar magnet or any other magnet for that matter, then it will have a north pole and a south pole. So it is impossible to construct a magnet which is having only one polarity. So if we consider something like this, that this is a bar magnet having north and south. So if I split this magnet into two halves, then the result will be a new north and south polarity, somewhat like this. And if we again split this magnet into two halves, the result will be north-south frame of a magnet. So I say that monopole never exists in a magnet. And the next thing is, or the last point, that the magnet is constructed using iron and its alloys. Magnets can be constructed or can be made using iron and its alloys. So these are the basic facts that must be kept in mind regarding the magnet. Now the next which we are going to discuss is about the magnetic field lines. So in order to initiate discussion about magnetic field lines, we first of all draw a bar magnet and the magnetic field lines associated with it. So we are considering that this is a bar magnet having a north pole and a south pole. So due to this, the magnetic field lines will be created which will be running from north to south. So the magnetic field lines is running from north to south. Down here also the magnetic field lines are running from north to south outside the magnet. Whereas inside the magnet, whereas inside the magnetic field lines are running from south to north. So it is important that the magnetic field lines are shown with the direction, and these are the magnetic field lines associated with a bar magnet. The field lines of a magnet or a solenoid forms a continuous closed loop. When I say it forms a continuous closed loop, I mean to say that outside the magnetic field lines will be running from south to north, and inside the magnetic field lines will be running from south to north. That is, they form a closed loop. Now, at any point on the magnetic field near a magnet, if we wish to know the direction of a magnetic field, then the direction is determined by drawing tangent to the direction of magnetic field line at that point. So this is the direction of magnetic field here. If I wish to know somewhere here, so it is determined by drawing tangent to the direction of magnetic field at that point. So the direction of the magnetic field at any point near a bar magnet is given by drawing a tangent on the magnetic field lines at that particular point. Now the next important parameter is the larger the number of magnetic field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. So the larger is the number of magnetic field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. So in this light, if I explain you, so if I consider a patch of area A over here, so we are having three magnetic field lines that is passing through it. And if I draw the same patch somewhere here, then the number of magnetic field lines that is passing in this case is 1. So the strength of magnetic field at A1 is greater than the magnetic field strength at A2. And the last important fact, that the magnetic field lines do not crisscross or intersect each other. The magnetic field lines do not crisscross or intersect each other. It is because that the direction of magnetic field at a point is obtained by drawing a tangent at the point on the magnetic field. So if the magnetic field lines are crisscrossing each other, then it implies that at one particular point there are two directions, which is simply not possible. So now we are going to discuss about a solenoid acting like a bar magnet, or a bar magnet act as an equivalent solenoid. So we are discussing a very important concept over here. So we understand it in a way like this. So the first thing which I wish to tell you is that the every current carrying loop, let me first of all put down the heading, bar magnet as an equivalent solenoid. So this is what we are going to study. So before this, let us first of all deal with what exactly constitutes a bar magnet. So when I say that the bar magnet is having a geometrical length L, So the magnetic length of the bar magnet is equal to 80% of the geometric length, that is, it is equal to 0.8 L or equal to 0.84. So this is the first important notable fact which must be kept in mind, that if I am considering this as a bar magnet, then the polarity or the north pole is situated slightly inside from the edge. So if L is the geometric length of the bar magnet, then the magnetic length of the magnet is equal to 0.8 L. This is the magnetic length of the magnet, which is equal to 0.8 L. Now this is behaving like a north pole and this one is behaving like a south pole. We represent the north and south polarity having a pole strength of positive m and minus m respectively. So the north pole is represented with a pole strength of plus m and the south pole is represented with a pole strength of minus m, and the separation between them we are writing it as small m. So I can say that a bar magnet is behaving like a small dipole. So a bar magnet behaves like a small dipole, and the dipole moment of the bar magnet can be written as, so the dipole moment for this bar magnet, if we wish to write the dipole moment for this particular magnet, then the dipole moment for this magnet can be written as, we are representing it with mu vector, or m vector can also be used. For the time being we are using mu vector. So it is equal to the pole strength multiplied by the separation between the two poles. And just like the electric dipole, the direction of magnetic dipole is also from the negative m to plus m. So this is going to be the direction of dipole moment or the magnetic dipole moment mu vector. So the direction is from the south pole to the north pole. The minus m to plus m. So this is important for understanding the concept which we are going to discuss in here, where m is regarded as the pole strength of the magnet. So if we consider a solenoid, so when we construct a solenoid, we construct it like this. So before establishing an equivalence between a solenoid and a bar magnet, it is important that we understand both of them in a connecting way. So I say that this solenoid consists of a large number of current carrying wire that is wound around a soft iron bar which is carrying current like this. So one thing is clear, that I can say that each current carrying loop will behave like a small magnet and will have its own individual magnetic moment. So when I say something like this, I mean to say that each current carrying loop that will be constructed over here will produce its own magnetic moment. Now why I am saying you this is because of somewhat like this. So if we consider that a loop is carrying a current in the clockwise sense, so we say that it is the south polarity. And when we say that the loop is carrying current in the anti-clockwise sense, So we consider it as the north polarity. So whenever there is a current carrying loop, so if I place any current carrying loop somewhat like this, considering that the direction of current is like this, so for an observer who is observing from here, I am calling this observer as O1, and the another observer who is watching this same loop from the other end, which I call as observer O2. So now according to the two observers, so according to the observer 1, he is facing the south polarity and is viewing that the loop is carrying current in the clockwise sense, but according to the observer O2, he is viewing the north polarity, because according to him the direction of current is in anti-clockwise sense. So it is important that you understand this concept first, that a single current carrying loop is also an example of a magnetic dipole. A single current carrying loop is also an example of a magnetic dipole, and this is something which must be understood. So over here I can say that each of this current carrying loop which we have drawn over here will behave like a small magnet. So each of this current carrying loop will behave like a small magnet, and all of them combined together can be replaced with a single magnet. So considering this, I am considering that this end is north pole and this one is south pole. Again for the another loop, north south, again north south, north south, north south, north south, and something like this, such that I consider that each length is equal to d. So if I say that there are n such current carrying loops, n such loops, so I will say that there are n such magnets. There are n such magnets, and if I say that the total length of the solenoid is equal to L, then I can say that n such magnets, each having a length equal to d, must be equal to the length L. This is the first mathematical equation which we have framed in this particular chapter, that if there are n such loops, then I mean to say that each current carrying loop will behave like a small bar magnet having a north and a south polarity with a length d, and if we combine n such small magnets, then it must be equal to the total length of the solenoid, which we treat as length L. And the pole dipole moment for each small magnet that we have considered over here will be written as the value of dipole moment for the magnet over here can be written as mu, which is equal to small md, where m is the pole strength of the magnet which we are considering. So now based on the concept which we have learned, we are considering a solenoid something like this. So we are considering a solenoid something like this. This is the central axis of the solenoid, and I am cutting it into two halves for our calculation purpose. So we are considering that the solenoid consists of n turns per unit length, n turns per unit length, and the total length be equal to 2L. So when I say that the total length is 2L, then I mean to say that this portion is having a length L and the other half is equal to here. So the total length is equal to L, and the radius of solenoid is equal to A. Now we consider that the value of A is very small in comparison to R. When I say R, I mean to say that we are calculating the magnetic field at a distance R from the center of such a solenoid at a point P on the axis of the solenoid, somewhere here. And we are considering that R is greater than A, and R is also greater than L. So in order to understand this, we are considering at a distance x, from the center, we are considering a patch of thickness dx. So we are considering a patch like this having a thickness dx. Now based on the formulation of turn per unit length, I can say that turn per unit length can be written as dn by dx over this small patch, and hence the value of total number of turn dn is equal to n dx. So if I write the expression for magnetic field due to this particular patch which we have selected, then the value of magnetic field will be written in this way, that dB is equal to mu naught n I r square. So number of turns is written as n dx I r square upon twice of x square plus r square to the power 3 by 2. So the distance in this case is going to be r minus x whole square plus a square to the power 3 by 2. So this is based on the result which we have learnt in the previous chapter, that the strength of magnetic field on the axis of a circular current carrying coil is equal to mu naught ni r square upon twice of x square plus r square to the power 3 by 2. So based on this result, we have written this particular formulation. Now in order to calculate the magnitude of total field, we need to sum it over the total length, that is from x equal to minus L to x equal to plus L, and hence I can write it as that the strength of magnetic field B will be written as mu naught NIA square upon 2, and we are left with this integral dx upon r minus x whole square plus a square to the power 3 by 2, and the limit of integral is from minus L to plus L. So we can solve this using trigonometric substitutions, but in this purpose we are not doing it using trigonometric substitutions. Rather we are using these approximation where we have stated that r is greater than a and r is greater than L. So if r is greater than L, then we can certainly imply that r is also greater than x, because x is smaller than L. So if I solve it using this, so I am solving the denominator portion first. So I am writing it in this way over here, that the value of denominator which we have, which is equal to r minus x whole square plus a square to the power 3 by 2. So we can approximate it in this way, like over here r is greater than x, so we can approximate in the first round that r square plus a square to the power 3 by 2. Now over here we again say that r is greater than a, so on further approximation we write it as r square to the power 3 by 2, which we write as r cube. So the denominator term can be replaced with a single parameter which is equal to r cube, and we can write it in this way, that the value of magnetic field B is equal to mu naught Ni a square upon 2 r cube, and the limit of integration dx is from minus L to plus L. So basically we have changed this formulation. So we have changed this denominator portion, the rest of this parameter remains unchanged, and then we are left with integration of dx, which we have from minus L to plus L, and over here the value will be obtained as mu naught Ni a square 2L upon 2 r cube. So this is what we obtain over here. So the magnitude of magnetic moment of the solenoid. So if I write over here the magnetic moment for the solenoid, magnetic moment for solenoid. So the magnetic moment for solenoid M can be written as INA. So I is I. The total number of turn will become N multiplied by 2L. This is turn per unit length multiplied by total length into area, which is pi a square. So this can be this entire term over here, IN2L into pi a square, which is over here this one. This entire term which is present in the numerator, which is equal to Ni2L into pi a square. So pi is missing over here. So in order to make it happen, I am introducing a pi parameter multiplied on top. So the numerator and denominator both are multiplied with pi. So the expression can be written as that the value of B is equal to mu naught M upon pi into 2 r cube. And we can modify this by multiplying by 2 on numerator and denominator. So we will obtain mu naught upon 4 pi 2m by r cube. So this is the expression of magnetic field at a distance r on the axis of a bar magnet, which we have obtained over here. So B is equal to mu naught upon 4 pi 2m upon r cube, where the value of m is this one, which is INA. So I is the current carried. The total number of turn is written as turn per unit length multiplied by total length, which is in this case is 2L into pi a square. So if we do this, we get the strength of magnetic field on the axis of a solenoid. So now we are dealing with the dipole in a uniform magnetic field. So we are dealing with a dipole placed in a uniform magnetic field. A dipole placed in a uniform magnetic field. So we deal with this in the same way we deal with a dipole placed in an external electric field. So if I suppose that this time a magnetic dipole is there, so I consider that the magnetic field is present in this region like this. That is, we mean to say that there is a large north pole on the left hand side and there is a large south pole on the right hand side. And if I fix a dipole or a magnetic dipole over here, which is having pole strength m for the north and south pole respectively, then such a dipole, magnetic dipole, can be placed like this. So this one is plus m and this one is minus m. So basically plus m is representing north polarity and minus m is representing south polarity. So now as a result of which it will start rotating or a torque will be generated. So a torque will be generated and we can say that the force which is acted upon by each pole is equal to mb. Just like F equal to QE, we are writing it as F equal to mb. And due to this, a torque will be generated, and in order to calculate the torque, we can take an IOR, that is instantaneous axis of rotation. And if I write it from point B, which we are mentioning as instantaneous axis of rotation, and we are considering that the pole length is equal to L, making an angle theta with the magnetic field. So the magnetic torque which is generated can be written as the force which is equal to mb, and there is a L sin theta component. And if we wish to write it in torque vector form, so we can write that m into L is regarded as magnetic moment m cross B. So we are writing it as M cross B, which is analogous to P cross E in case of electric dipole. So we get a value of equivalent to torque, which is equal to M cross B, where M is magnetic moment and small m is pole strength. So small m is pole strength and capital M is magnetic moment. So in this case, if we wish to calculate the time period, so we are writing it in this way, that the torque generated. So if we wish to calculate calculation of time period, so we can write it over here in this way, that tau, which is equal to m cross b, can be written as mb sine theta. Now we are writing for theta to be very small. We can say tau, which is equal to I alpha, is equal to minus mb into theta. So alpha can be written as minus mb by I, square root square into theta, and the time period will come out to be 2 pi root over I by mb. So this is the value of the time period of a magnetic dipole placed in an external uniform magnetic field B. So we have deduced it or converted it into the form of a SHM. So it is a form of SHM where we have attained that alpha is equal to minus omega square theta, and hence we write over here that T is equal to 2 pi root over I by mb.